SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. Let's get back to the continuation of our lecture on devising the higher order elements for 2 dimensions. We have seen 2 types of approaches, the Lagrangian approach, Lagrangian elements, and then we also looked at the serendipity. Serendipity is people have devised the shape functions and just by chance. So that's why the serendipity is there. So to start with, we have 8-noded serendipity element, which has only the 8 nodes on the boundary here. And then, so similarly, I'll talk about this one. So there's also another next one is 12-noded cubic element. So this 12-node cubic element has 12 nodes on the edges like this. One, 2, 3, 4, 5, 7. So I hope the locations are known. So these locations are -1, -1/3, +1/3, and 1. Okay, in the zeta direction. So this we still call it serendipity, 12-noded. And what is its behavior? So the behavior is, again, this is cubic, and compared to Lagrangian, which has 16 nodes for the same cubic behavior, this with the 12 nodes only, it has the cubic behavior. So here also we can have up to 12. So these you can have it from the textbook. Many books are available. In fact, they can be derived also. There are certain procedures. So for the moment, let's assume that they're there. We want to really actually understand how these things have been constructed. So that's or which are the terms that are present here. And let's compare only this cubic thing. Again, going back to the Pascal's triangle. Writing these things. So what is the difference between so for the Lagrangian, so if you recall, so all the terms here up to here So this is the Lagrangian. node, so which has the behavior of cubic, okay, and only the cubic polynomial is complete here. Whereas in this case, what we have here is that there are only 12 terms. And what are those 12 terms? So those 12 terms are these, which are enclosed by. So these are the 12 terms that are present. So this additional 4 terms have been eliminated. Okay. So this way, if you look at the cubic polynomial, this third row, so is complete just like in the Lagrangian also. In the Lagrangian also, only cubic was complete. There are higher terms here, but which were incomplete degree polynomial of that row, right? So that way, this 12 node serendip element is as good as 16 node Lagrange element. Okay, so this is as good as 16 node Lagrange elements. So that's why these serendipity elements are much more popular, because they have less number of nodes and the behavior is as good as the Lagrange element. So in fact, you can even go for the next one, 4 into 4, 16. So that may consist of all these things for Lagrange, but for this one, so then it will not have all the 60, all the, what is that? That is, the next one is 5 into 5, so that is 25. So out of which there are many nodes are eliminated. So these things you can see for yourself, or all these things can be actually, there is a method in that sense that there are Lagrangian polynomials on this side and linear on this side, or constructed like this, and that's for the non-corner nodes. And for corner nodes, you have the bilinear, only the bilinear are there, and on which the manipulations are done. So you can just look into any book, any textbook for this one. Okay, so this is how we construct the serendipity elements. Okay, so now there are another very popular elements, which are the triangular elements, two-dimensional triangular So in the triangular elements, so what we had used the triangular element with 3 nodes, which was linear in nature, right? And the 3 terms. So the first one was linear element. So the linear element was just 3-noded triangle. IJK, or now we can use 1, 2, 3 also. So which was just let's use I. Okay, so this is how we use this one. Then we had The next one is quadratic element. So the next one is quadratic element of 6 nodes, okay, which has the 6 nodes are 1, 1, 2, 3, 4, 5, 6. So these are the 6 nodes. The beauty of this triangular element is that the number of terms that are needed here symmetrically placed are just right number to complete the terms here, polynomial terms, either 3 or 6 or 10, something like that. So we will just see that these 6 terms here, if you go back, maybe I have to draw, I'll put that Pascal's triangle again here. I'll do the Pascal's triangle again here, just for the triangle's sake. So we have x, y. Alright, so I wrote them again here. Is that for 3 nodes, so for 3 nodes here, we require 3 terms. So those 3 terms are this, right? For the next one, for 6 nodes, the terms that are used are these are just the 6 terms that are needed, and those 6 terms are these 6. And like that, the next one will be quadratic and cubic. I'll just put it here. I'll just show you how to construct these things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, and also we have 10. So what are these 10 terms that are necessary here? So the 10 terms that are necessary here for cubic is this one up to here. You can see that for this to complete, we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we require 10 terms, and then we require 10 nodes. So this requires 10 nodes. So how do we place them? So we have to place them systematically. So that's the 1, 2, 3, 4 vertices, and the 4, 5, 6, 7, 8, 9. And we required one more term here, that is the 10th node, which we usually put it in the center. Okay. So that is how we put it, the 10 nodes. Okay. So that way, the beauty of this triangular element is that we just have enough number of nodes or terms which completes the polynomial here. So for linear to complete here, we require 3 terms. For quadratic to complete here, we require 6 terms, so 6 nodes. And to complete this one, we require 10, and we have put 9 very nicely, and only one additional node in the center, 10th one in the center. Okay. So like this, in fact, you can even go for the next one. If you see that, if you go for quartic, so quartic requires how many? 10. Okay, 1, 2, 3, 4, 5. And 10 plus another 5, we require 15. So you should see how you can put the 15. So how do we put 15? So can we see that? So 15 is that we put 12 outside and 3 inside. just 3 inside. So the internal nodes are also not many. Okay. So this is that way the triangular element is the most efficient element compared to these rectangular elements. Rectangular or even, though of course serendipity element is used. 8-node serendipity element is again a very popular element because it's a quadratic and rectangular element. And here for quadratic you just require how many? 6 nodes. Okay, where you required 8 nodes there. Okay. Anyway, it has serendipity element has got one more advantage. We will see it in connection with parametric elements. So just to complete the triangular element, how do we develop the triangular element? Rectangular element we know how to develop because we take the Lagrangian element and taken the products. But this triangular element requires a slightly different approach. So the development of triangular element requires, since we have so we do everything in terms of xy because either the derivatives or the integrations are with respect to xy. So we'll have to see how we can transform between xy and suitable coordinates. So the natural coordinates just like we use xi and eta for the rectangular element. So here we use some other types of natural coordinates known as L1, L2, 3 coordinates are used here. So that means that every point here P is represented by xy or L1, L2, L3. So xy in the Cartesian coordinates is equivalent to natural coordinates L1, L2, L3. So what is the transformation between these two? So we'll see that though this is only 2 coordinates, this is 3. So that means that there's one arbitrary relationship, that is the sum is equal to 1 and x is equal to x1, L1, x3, L3, and y is y1, L1. Okay, so that is the transformation between xy. I mean, knowing L1, L2, L3, this is how we get xy. So what we can write here is the relationship between xy and L1, L2, L3. This L1 plus L2 plus L3 is equal to 1 is some arbitrary relationship which is useful as well, which is gives some sort of symmetry for this one. Okay, so we can do the inversion and find out. So in fact, L1 turns out to be this is the determinant twice the area. So this is A1. If you recall our definition of B1 and C1, BI, CI and all that, So this exactly has the same form as that, so we can as well use that. So if you know A1, B1, C1 in terms of x1, x2, x3 and any xy here, so you can find out L1. So similarly L2 you can find out. So this is the transformation between the given xy. You can find out L1, L2, L3 in this manner, okay? And given L1, L2, L3, so you can find out the xy also. So these are two relationships, so we can find out between these. And so this is the coordinates. And then we have the shape functions. The shape functions, so linear, three node linear. So you have N1, N2, N3. So where, if you recall, so N1, if you recall our original shape functions, so N1 was A1 plus B1x plus C1y, A2 plus to C3y. So if you recall, so that means that this N1, N2, N3 for the linear one in terms of xy. So this is what we have. And now these are nothing but, you can very clearly see that these are nothing but L1, L2, L3. So once you know the natural coordinates L1, L2, L3, then the shape functions are nothing but, so N1 is L1, N2 is L2, and N3 is, so these are the shape functions for the three nodes. Very simple, right? Very simple shape functions. In fact, these natural coordinates also has, so we can also give a meaning for this natural coordinates here. From looking at this one, this is determinant as well as it is twice the area of the triangle, you can very well see. And then L1, if you recall, so that means that if you want to get L1, so it is nothing but the first column will replace by xy, and so using the Cramer's rule, so this is how it looks like by the determinant itself. So what is this L1 means then? So L1 means that this is nothing but one, two, three. So this is nothing but, if you have the point P here, xy, so this is nothing but the area of the triangle, twice the area of this triangle, and this is the total area, twice the area of the total triangle. So if you call this as A1, then L1 is nothing but A1 divided by total area A, and A2, so this is A2 and this is A3. Okay, so area A1 is nothing but area of P x2 P2 3, like that. So this is A2 by A. So thus this is also called the area triangle. So this L1, L2, L3 are also called area coordinates. So this is very convenient. So L1, L2, L3 can also be represented as the ratio of the areas. So the first one is like this, right? This is linear. And the next one, quadratic, shape functions for quadratic, 6 node functions, okay, or numbered like this, 1, 2, 3. In fact, you should know the coordinates of each of these vertices. For example, node 1, what is the 3, L1, L2, L3 for this location? So node 1, this is the 1, 2, 3 is the area A1, as well as it is the total area. So thus, so it is L1 is 1, L2 is 0, and 1, 0, 0. So similarly, this is 0, 1, 0. This is 0, 0, 1. So each node is represented by 3 natural coordinates. So like this, we have here. For quadratic, we also have more terms, more nodes, 4, 5, 6 at the locations. So you can find out here that node 4, what is its node 4? Its first natural coordinate is 0, and the other two are half and half, because it's half area. So similarly here, 5 has half, 0, half, and this is 0, half, half. So you can go from one to the other very quickly, like this one. So you can find out here, node 1 has the shape function. Node 1 has the shape function. I think I'll just give you. So it is L1 to L1 minus 1. So in fact, it should be a quadratic to 2 appearing, as well as it should have a node, a value of 1. Obviously, if you put 1, 0, 0 in this one, L1 is equal to 1 if you put it. So this is equal to 1, as well as if you put any other 0, 1, 0. So where L1 is 0 and here also L1 is 0. So similarly here, so anything here, so 2 L1 minus 1 here. So it will be 0, okay, for others also. For these nodes 4, 5, 6 also it is 0 except at node 1. So similarly you have L2 and N3 and L4, for example. L4 is 4, L2, L3. L5 is 4, L1, L3. Okay, many times all these things can be constructed by just looking at the location as well as that its property of the shape function. So like this, the shape functions can be, these are not L4, I'm sorry. These are N4, N5, N6, sorry. Okay, so once you have the shape functions, so quickly, if you want to find out this difference matrix, or for that matter, if you want to find U, so this is nothing but N1, U1 up to N6, U6, and V is N1, okay, and B matrix if you want, so it is epsilon X, epsilon Y, gamma XY. These are the derivatives which you will have with XY. So like this you have, and this is nothing but dou n1 by dou x 0. So you will have u1 v1. So this is the usual procedure which you have to get. Only thing there is that any function if you want to take a derivative with x, so that is n1. First you take it with n1, and n1 with x is nothing but b1, and n2 which is b2, and n3 b3. Okay, so like this you can convert the derivatives. I'm sorry, this is L1. I'm sorry, these are L1. Take the derivatives with L1 and then convert it into x. So like this, so you can get the derivatives in x, and then of course there is also a small integrations. I'll just give it. So there is an area integral. The things which you have it in terms of L1, L2, L3. If you want to do this over the area, okay, so this is another useful thing for doing the integrations. Okay, so I just gave the power of the triangular element, and also I gave the procedure how to evaluate many of these derivatives and the integrations. So otherwise the procedure is all same. You can go ahead. This is B. Once you have that B, so you have to do B transpose dB to get the stiffness matrix. Okay, so I think that gives you an idea how to evaluate the matrices for the triangular element. So I think I'll stop here for this 2D element evaluations of various matrices. So then I hope you can proceed. All the rudiments, all the important points are here. You can continue and derive all the necessary matrices. So for the moment, so we'll take a pause and bye for the moment.